So the first part of this talk will be about. The first part will be about the mapping class group. So we'll introduce the notion of the mapping class group, just to define the notion of pseudo-Anosov homeomorphism. So and then we'll talk about how to construct pseudo-Anosov using Origamis, and we'll also see. Then we'll switch to the character variety and the representation variety. And in the second part, we'll talk about some previous results, and we'll try to give ergodic examples on the character variety, and at the end we'll give non-ergodic example. So let's consider S to be a closed surface. So in all the talk, S will be a closed surface, and we consider the group of all homeomorphisms of S, and we take the homeomorphism that preserve the orientation. And so this will be the group we'll denote it by homeo plus of S. And we'll take the group of all homeomorphisms that are isotopic to the identity, and we'll denote it by homeo 0 of S. And then the mapping class group will be just the quotient group. So mod S would be, we take all the homeomorphism of the surface and the quotient by relation of equivalence. So if two homeomorphisms are isotopic to each other, so they are in the same class. So as a first example, we'll talk about what is the mapping class group of the torus. So actually the mapping class group of the torus is isomorphic to SL2Z. Because if you take any homeomorphism on the torus that preserves the orientation, you can do an isotopy on the surface in order to make this homeomorphism an affine transformation on the torus. And so since we have an affine transformation on the torus, we have only three cases. So either A is elliptic and they are finite. So we have only finite matrices that are elliptic, or A is parabolic. For example, you can take on the torus, you can take the matrix 1, 2. Let's say this one, 1, 1, 1. So this is a parabolic matrix, and we can see that it preserves this loop. So it fixes this loop. So we have this, or A is hyperbolic, which is the generic case. So we have A is hyperbolic, means that we have two foliations. So that means that the matrix have two eigenvalues, lambda minus 1. So if you take the eigen directions here, so they will define a foliation on the torus. And what does the hyperbolic matrix does? So it expand by one part by lambda and extract the other by lambda minus 1. And actually this picture, so we have the same picture in for higher genus surfaces. And this theorem is due to Nielsen and Thurston. So if you have a homeomorphism S on a closed surface where G is bigger than 1, then at least, so we have only three cases here. So we have that either H is periodic, which is not very interesting. So, and the second case is H is reductive. That means that H fixes a simple closed curve. So since H fixes a simple closed curve, so you can cut along this closed curve, and then you have new two homeomorphism on each part after cutting. So in other words, so we reduce the homeomorphism to other surfaces of lower genus. And the last case is H is pseudo-Anosov. So we'll see. So we'll define later what is exactly a pseudo-Anosov. So for example, an important examples of reductive homeomorphism are the Dehn twists. So if you have a simple closed curve on the surface S, so what is the Dehn twist? So we take the curve gamma here. So this is our curve gamma. And then you take a tubular neighborhood of gamma. So this is a tubular neighborhood. And if a curve passes through transversely through this tubular neighborhood, so it does turn. So it turns one turn along the curve gamma. So this is what happens in the tubular neighborhood, and it is actually the identity elsewhere. So it really, for each curve gamma, you can construct this homeomorphism. And actually, the Dehn twist, if you consider, so you can, there is a theorem that, so you can generate the mapping class group by Dehn twists. So you can take many curves, and in this way you can actually generate the mapping class. And this is the important example of predictive homeomorphism. Now we move to the pseudo-Anosov, and in order to define the pseudo-Anosov, so we first define what is a half translation surface. So a half translation surface on S is an atlas where the transition is an atlas defined only on S. So it's defined only on S minus sigma. So you remove a finite number of points, and on this, after removing the point, you will so you'll get that. So this atlas verifies that transition map is a half translation. So that means it is of this form. And if you define this atlas on S minus sigma, so we'll have so you can pull back the metric. So you will pull back the metric on S minus sigma, and then you can extend the metric on S everywhere. If you extend the metric everywhere, we'll ask that the singular point here should be conical singularities. So they are conical singularities of angle. So the angle here is k times pi, where k should be bigger than 2. If you assume that k is bigger than 1, there will be some problems after. And now pseudo-Anosov homeomorphism is a homeomorphism, and after you take an isotopy, you can make H to be a hyperbolic affine transformation on this on a half translation surface. So you see that if you have a half translation surface, then SL2Z acts on SL2R acts on the half translation surface S. And we consider only these element in SL2R that brings back the structure, the half translation structure. And the pseudo-Anosov is an element, is you can see it as a hyperbolic element, a hyperbolic matrix, such that there is a half translation surface where when you apply this hyperbolic matrix, you go back to the translation surface. And so you can see that they are, so these pseudo-Anosov are cousins of the Anosov transformation of the torus. And so as example, we can take, so for example, this is a half translation surface. So in this case, it's translation surface because we glue this one to this one, and we glue this one to this one, this one to this one. So it's a half, it is a translation surface with one singularity. So we have only this one singularity. And if you compute the total angle, you get 6 pi. And if you notice, so maybe you notice that this is a ramified cover of the torus of the Griffey. So in this on this translation surface, so what we will define? We'll define this loops V1 and V2 in red, and we'll define H1 and H2 in green. So if you take the Dehn twists around V1 and the Dehn twist around V2, so you can see that we can realize this Dehn twist as an affine transformation. So if you take the matrix 1, 2, 1, 0, so what it does, it fixes this edge, fixes everything here, it fixes everything here, and then it rotates. If you take any edge, if you take any line here, so it perform a rotation here, and then the rotation, the angle of the rotation varies. So we start with 0 and then end up with 0. And the same thing happens here, since we took 1 to 1, 0. So it fixes this one, but the angle here is double. So actually you can see that the Dehn twist here, tau h1, then you compose it with tau. You take tau v1 and you compose it with tau v2 to the power 2. Then this homeomorphism is realized as an affine transformation of the translation surface. And the same thing happens to h1 and h2. So we can see that the matrix 1 to 1 and these two matrices are affine transformation on S that realize exactly this composition of Dehn twists. And so if you take the composition of all these of the two homeomorphisms here, so you get a pseudoanism, because if you compose the matrix, you get a hyperbolic matrix. And this is exactly the definition of this. Does agree exactly with the definition of pseudoanism. So we have so this is a way to construct this is an example of a pseudoanism. Actually, one can remark that the pseudoanism map cannot be reductive. So if you take a pseudoanism, it cannot fix a simple closed curve. Why it cannot fix a simple closed curve? Because we can use the following fact, that if you take F pseudoanism, then the intersection number, if you take A and B, two simple closed curve, then you have that the intersection number of Fn applied to A and B. So if you take the geometric intersection between these two curves, and you take this to the square root of n, this will converge to lambda, where lambda is the expanding factor of the hyperbolic matrix associated to the pseudoanism element. So that means that it cannot fix a simple closed curve. And now one way to define many pseudoanism homeomorphism is the notion of origamis. So what is an origami? An origami is just a ramified cover over the torus, where we have only one singular point on the basis. And why we can exactly as the previous case, we can generalize it. It's just a generalization of this case. So we have, if you take two multi-curves, let's say, so what do we mean by a multi-curve? So multi-curve that, so for instance, C here. So that means that we have many curves where we don't have intersection between them. So we have this curve, let's say this curve. So C1, for example, C2, C3. So if you take two multi-curves, such that, and we assume that these multi-curves are filling. What is the meaning of filling? That means that if you take all the curves in the two multi-curves, they are in minimal position. So the intersection, if you see the intersection, you will get, at that position, you get exactly the geometric intersection between them. And we assume also that, so the meaning of filling also asks that when you cut along this curve, you get only a union of these. And actually, if you have two multi-curves, two filling multi-curves, then we can always associate an origami on them, such that every C1 argue with HI. Let's say every CI argue with the HI. It's exactly the HI on the origami. And remember, HIs, so HIs are or VIs. So they are the loops that corresponds to the cylinder. So if you have, let's say if you have an origami like this, yeah. So if you have V1 will be the curve that corresponds to this vertical cylinder. So if you have an origami, you can always decompose it to horizontal cylinders and vertical cylinders. And the VIs and the HI are defined to be these loops that generate the fundamental group of the cylinder. So if you start with two film multi-curves on the surface, you can always construct an origami where the CIs are exactly the VIs and the DIs are exactly the HIs. So to do this, let's consider surface S. Yeah, so this is, consider our surface S. And if you have, let's say this is CI, and it intersects here, DJ here, at the point P. So we can always consider. So what we will construct here, we will consider a square that in this way. So centered at the point P, and then if you do this at all the intersection, what we will get at the end, you will get an origami. So we'll translate to an Euclidean, let's say, Euclidean square. And then you glue the square together, following the combinatorics from the two multi-curves. So you continue like this, and then you glue here, and so on. And actually, an origami, so an origami is always you can see it as many squares, and then you decide. So an origami, you can see it always as, let's say, these squares here, and you decide what edge goes to which edge. So let's say this one is identified to this one identified to this one to this one, and so on. So that means that multi-curves, you can see it as, if you have two multi-curves, you can see it as an origami. And now we will move to another notion in this talk, which is the representation variety. So a representation variety, so it is a space of all homomorphism from the pi1 of S G to a Lie group G. And in this case, we take the Lie group to be SU2. So you take it you take all the homomorphism from the pi1 to the group. And actually, this gives us an algebraic variety, which is irreducible. So denoted by hom pi1 of S SU2. And if you have a representation in the hom variety, so we have three possible cases. So either rho is irreducible, that means that rho fixes no direction in CP1. Otherwise, if the image fixes the same vector on CP1, that means that rho is abelian. That means that rho, the image of rho, lies in one parametric subgroup in SU2. And remember that the only subgroups in SU2 are the one parameter subgroups. So this implies that, yeah, if it fixes one direction, that means that it is abelian. And the other case is that rho is central if the image is in the identity or minus the identity. And now if you have, on the representation variety, SU2 acts by conjugacy. So if you have G on rho, so it's exactly G rho, G minus 1. And if you take the quotient, is called the character variety. And actually we have an action of the automorphism group of the pi1. So if you have an automorphism, let's say phi, an automorphism the pi1 of S. So then you can pre-compose. So if you take the automorphism and then you compose it with rho, and this will give us an action on the hom variety. And if you take an element, a homeomorphism phi such that phi is isotopic to the identity. So this means that phi on the algebraic level, on the pi1 level, is just a conjugacy by some element. So it is in the interior of the pi1 of S. And this implies that if you take a homeomorphism that is isotopic to the identity, then its action is absorbed by the conjugacy action of SU2. And this implies that the mapping class group acts on the character variety. So what we have here, we have an action of the automorphism group on the representation variety. And we have an action of the mapping class group on the character variety. So now we'll discuss a simple action. And this simple action, we'll just discuss if you take a simple closed curve, non-separating one, let's say alpha is a non-separating curve, then using the HNN extension, you can always write the pi1 of S in the following way. So we write it as the pi1 of S minus alpha. And then you add an element beta here, such that we have that beta alpha plus beta minus is equal to alpha minus. So we have these as a generator of the pi1 of S with only this relation. And what is alpha plus and alpha minus are the two curves after cutting. So this is you can see it as alpha plus. And this curve, you can see it as alpha minus. So a Dehn twist on this, after writing the pi1 in this way, you can see that the Dehn twist action on the pi1 is just a multiplication by alpha plus. Therefore, we have that the action of the Dehn twist on the representation variety. So the image of rho by tau of alpha, if you apply it to a curve gamma, so we get rho of gamma is if the curve gamma is in the pi1 of S. And if gamma is equal to beta, so you just multiply by alpha plus. And we can do the same thing actually in the case of if the curve is separating. So if the curve is separating, so let's say C is separating. Then you will write the pi1 of S as an amalgamate product, sigma 1 and sigma 2. So sigma 1 and sigma 2 are the two surfaces after cutting. So this is sigma 1. Let's say this is sigma 2. So write it as an amalgamate product with the only relation that C1 on the pi1 of S is equal to C2 on the pi1 of S. And tau alpha applied tau of C applied to rho applied to gamma is equal to rho gamma if gamma is in the pi1 of sigma 1. And it is just a conjugation by C if gamma is in the pi1 of sigma 2. So it fixes the first surface and it conjugates the other by rho of C. And actually this allows us to define, so the idea here is instead of seeing the Dehn twist as a discrete action on the home variety or in the character variety, we'll see it as a flow. And the way to do this, we'll replace, so if you take a representation rho, we'll take this group here, this one parameter subgroup, to be the group that passes through. So here is the identity. And here we have rho, let's say this is rho alpha. So we take the one parameter group that passes through rho of alpha with velocity 1. And so the action here will have an action of an S1 action on the representation variety. And instead now multiplying by rho of alpha, so we multiply by the whole subgroup. So at the time t, will multiply by the point t in the subgroup multiplied by rho of alpha, rho of gamma if gamma is equal to beta. And now this gives us a flow on the representation variety, and this flow is very important. So if you take so one remark, you can see that the orbit of the Dehn twist are contained in the orbit of the Dehn, and this we call it the Dehn twisted flow. And you can see that the orbit of the Dehn twist is contained in the Dehn twisted flow. And second, if you take the projection here defined, so we'll always have a projection here, rho p of alpha. So such that if you apply to, so rho of p of alpha applied to rho is just the restriction of rho on s minus alpha. So if you take this projection, now this will define an S1 bundle over the Hom variety of the pi1 of S minus alpha, where the fiber are exactly the Dehn twisted orbits. So you can see, because the Dehn twisted orbit does not change the representation at the pi1 of S minus alpha. So it fixes that and change everything else. And this exactly coincides with, so the fibers and the orbits coincide. And so this will be the end of the first part.
Okay, thank